Alkynes are the carbon compounds that have a carbon-carbon triple bond in them. What we're going to do is learn about their properties, physical properties, and one chemical property in this slideshow, and also learn the basics of nomenclature. Alkynes, because they have pi bonds, are unsaturated. They are very much like alkenes, except instead of having just one pi bond in an alkene, there are two pi bonds. Each carbon is sp hybridized, and because it's sp hybridized, the bond angle between the carbon, hydrogen, and the carbon-carbon bond is 180 degrees. In the next slide, we're going to go into the bonding arrangement here, a little bit greater detail. But if I look at this bond here, this is an sp orbital. Excuse me, let me point at it for you. If I look at this bond right here, this is formed by an sp orbital from the carbon to the s on the hydrogen. This bond here is formed in the same way, an sp orbital from the carbon with an s from the hydrogen. Because the carbon is sp hybridized, the sigma bond in here, which I'm just picking one of these and calling it a sigma bond, is sp overlapping with sp, and that's the sigma bond here. That leaves two leftover p's on each carbon, a p and a p. And what do is they overlap. Here's another p over here, and it overlaps and makes a pi bond here and then a pi bond here at 90-degree angles. So there's two pi bonds and one sigma bond between the two carbons. The pi bonds are at 90-degree angles to each other. Because there's a leftover p, let's say, in the plane, and then a leftover p coming directly out at you at 90 degrees to the page and 90 degrees from the carbon-carbon bond axis, you will have those two p's, one here in the plane, one here in the plane, overlapping like this to form one pi bond. And then on this one, we have a p orbital that's coming directly out at you and going behind the page, and one on this carbon coming directly out at you and going behind the page, and they overlap side to side to form these two halves, one half and the other half of the pi bond. So one half up here and one half down here of the pi bond. This actually forms a tube of electrons around the carbon-carbon sigma bond. And so it's a very symmetrical shape, and we have triple bond strength here. The two pi bonds are at exactly the same energy as the other one, and the pi bond itself, in one pi bond in this carbon-carbon triple bond, is at the same energy essentially as a carbon-carbon pi bond in an alkene. And so as a result, the alkynes have very similar reactions to the alkenes. They really can do it twice instead of just once. Physical characteristics are very much like the alkenes. They are nonpolar and hydrophobic. There is no real dipole in a symmetrical alkyne, and so they're very nonpolar. And the lack of oxygens or nitrogens make them highly resistant to dissolving in water. Because the intermolecular attractive forces that are present in the alkynes are only van der Waals forces, we have low boiling points and low melting points for the molar mass of the molecule. The pi bonds are high in energy, just like the alkene pi bonds are high in energy, and as a result, pi bonds in the alkynes are reactive. And we see the kind of reactions that alkenes do occurring also in the alkynes, and we'll go through those in another lecture. One thing that is very different from the alkynes from the alkenes is that terminal alkynes, that means an alkyne that is at the end of a chain, have a hydrogen attached that is somewhat acidic. It is acidic enough that you can get very strong bases to deprotonate it. And we'll go into the bases that are required for deprotonation later on. Where does this acidity come from? Well, first thing that we're going to go through is compare the bond length and strength of the carbon-carbon bonds and the carbon-hydrogen bonds in ethane, ethene, and ethyne. If I look, you can see that the carbon-hydrogen bond for ethane, ethene, and ethyne are progressively getting shorter. And that's an indication that the bond strength is increasing. So as you go from ethane to ethyne, the bond strength of the carbon-hydrogen bond is actually getting stronger, as is the carbon-carbon bond length. If you look as you go from ethane, where it's a single bond between the carbons, to ethene, where it's a double bond between the carbons, to ethyne, where it's a triple bond between the carbons, you can see it's getting shorter. From this information, we can see how the bond length correlates with the dissociation energy in these molecules. Look at the carbon-hydrogen bond strength. See, this is the energy that it takes to separate these into two free radicals. So to break the bond homolytically and make it a carbon-free radical and a hydrogen-free radical, it takes 410 kilojoules per mole. To do that for ethene, a hydrogen on a carbon-carbon double bond, it takes even more energy. And the most energy of all is to break the carbon-hydrogen bond in an ethyne molecule. And you can see the carbon-carbon bond strength is also increasing from the single bond to the double bond to the triple bond. To cut the carbon-carbon bond, whether it's single, double, or triple, takes progressively more energy as you go from single to double to triple. It only makes sense there. But we also see that the carbon-hydrogen bond strength is increasing. Why is that? That's because you're going from an sp3 hybrid here to an sp2 hybrid to an sp hybrid in the carbon-hydrogen bond. And so you're getting lower and lower energy, so making a stronger and stronger. This information shows us where the acidity of a terminal alkyne comes from. Let's just look at the hybridization of each of these. Ethane has a carbon that is sp3 hybridized. Ethene has a carbon that is sp2 hybridized, and then ethyne has an orbital that is sp hybridized. As I go from ethane, which is 3/4 P, to ethyne, which is only 50% P, what you find is you have less P character in these orbitals, less percent amount of P in each of these orbitals. An s orbital has lower energy than a p orbital, so as you go from sp3 down to sp, you are actually lowering the energy of that orbital that is entering into the carbon-hydrogen bond. Well, this is important to realize how it affects the acidity of the ethyne. The pKa, as you go from ethane to ethene to ethyne, is getting lower and lower, meaning it's that as you go from ethane to ethyne, it's becoming more acidic. Why? it becomes easier to remove a proton, not because the bond strength is lower, but because the resulting anion is lower in energy. Ethane has an anion with the non-bonding pair residing in basically a naked sp3 orbital. The ethene anion has electrons residing in a naked sp2 orbital, and then ethine has electrons residing in a naked sp orbital. Because this has only 50% p compared to the others which have more p, the energy of those electrons is actually lower. And so it's easier to break the bond because the drop in energy, or excuse me, the increase in energy needed to form the anion is nowhere near. Okay, let's look at a deprotonation reaction. Potassium hydroxide, even though we consider it to be a strong base, is not strong enough to remove quantitatively remove a proton from an alkyne, a terminal alkyne. There's an equilibrium there, and you make a small amount, but the majority of the alkyne remains protonated. And why is that? That's because water is a stronger acid than the alkyne. However, if I look at sodium amide, when protonated, forms ammonia, and the pKa of ammonia is 36. The pKa of an alkyne is, terminal alkyne is around 26. This means the alkyne is a stronger acid, and so deprotonation is quantitative. The boiling point of the alkynes is very similar to that of the alkenes, maybe slightly higher. Why slightly higher? Well, that's probably due to the pi bonds in the alkynes having greater polarizability, so allowing greater van der Waals. Alkyne nomenclature is very similar to alkene nomenclature. Instead of adding an ene, we add an ine. If you have more than one triple bond, you would use diine or triine. If you have both an ene and an ine present, we use the format of ene-ine. Of course, you have to number where they are. We'll go through several examples to try and hone this down, but always remember to find the longest chain with the functional group. As we learned last semester, enes are subordinate functional groups to functional groups that contain oxygens and nitrogens, and so are ines. Find the longest chain containing the functional group, and then set the numbering system to give the lowest number to the functional group. Ines are subordinate to enes, so if the numbering for the ene and the ine have, if you're trying to determine which one is going to get the lower number, if they have the same number in either system, you choose to give the ene the lower number. However, you always want to have the lowest number functional group for either the ene or the ine if it ends up that they are different. And we'll go through examples on this to explain what I just told you. And then, of course, you would name and number the substituents. Here's an example of simple nomenclature with an alkyne. This is an internal alkyne, not a terminal alkyne. Terminal means it's on the very end. Internal means it's in the middle of the chain. I find the longest chain with the alkyne, and of course that's going to be 7 carbons here. So that's going to end up giving us heptine. You would choose to number the ine, giving the lowest number from the end of the chain. From this end it would be 4, and from this end it is 3, so we will call it 3-heptine. Now we name and number the substituents. There's only one substituent, a methyl, and it's on the number 5 carbon, and so it ends up being 5-methyl-3. Here are some other examples. Let's find the longest chain here, which has the functional groups. So if I look at this, the longest chain is actually 7 again. It is not going to be this long chain or this long chain. You have to pick the chain that would have all the functional groups in it if possible. So I go and I pick this as my longest chain, which is heptene-ine. Now I'm going to call this 1-ine and 5-ene because 1 is a lower number. And of course you can see there is a substituent, a butyl substituent, so it's 1,2,3-butyl, 1,2,1-ine, and 5-ene, and then you can see these are cis, so I want to also say cis, 3-butyl, 5-heptene, 1-ine. If I look at this, now my longest chain is this long one with the ine and the ene both in it. So if I look at this, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be none-ine. And we will give the higher priority to the ene because it's only 2 from the end versus 3 from the end here. So this is cis, 5-ethyl, 2-nonene, 6-ine. Okay, go ahead and try to name these. Pause the lecture, try to name these, and then after naming them, we'll come back and go over them. Okay, to name this first one, what we're going to do is we're going to find the longest chain with the functional groups. So 1, 2, 3, 4, 5, 6, 7 is the longest chain with the functional groups. And we're going to name it heptadiene-ine. We're going to number this one 1 for 2 reasons. Ene has priority over ine when the numbers are the same, but also 1, 2, 3 versus 1, 2, 3, 4 from this end. This second ene has to have the lower number also. So this will be 1, 3 heptadiene-ine, and then the ine is on the number 6 carbon, so that would be 1, 3 heptadiene, 6-ine, and then we have a butyl on the number 4 group, so that would be 4-butyl. So 4-butyl, 1, 3 heptadiene, 6-ine. We also, if we wanted to be really specific, if you notice this group is on the same side as this group, and those are the 2 high priority groups on the alkene. So they're together on the same side, so we can actually put Z in front of this to specify the geometry of this double bond. If I look at this alkyne, I can see this is my longest chain with the functional group in it. So 1, 2, 3 is propyne. Where is the cyclohexyl substituent? Well, since this is 1, 2, 3, it's going to be on the number 3 carbon, so we will call it 3-cyclohexyl 1-propyne. If I look at this, I can see there's an ene and an ine. The ene has priority over the ine, so we're going to name this as a cyclohexene. The substituent is 1, 2, 3 on the number 3 carbon, and it's a propyne, so we will call this substituent propynyl. Where is the ene? You always number from the point of attachment, which is right here. This is the number 1 carbon, so that's the number 2 carbon. So we will call this 3 parentheses 2 propynyl, close the parentheses, and then cyclohexene.